Hello, in this section, we will look at some summary of integration techniques, some integration strategies, and we will practice some selected integrals. Okay, let's see what we know. First of all, that's the list of integration formulas. We can also say they are almost all of them are the direct antiderivatives. Basically, we're reversing differentiation. We can see a little bit of U substitution. You can notice for the natural log or inverse tangent, all of the trigonometric one, but that's the formulas that we know. Integral of tangent of x dx, it's not a exactly direct antiderivative because we do not know right away what is the function that its derivative is tangent of x. But when we use the U substitution, we remember the formula was natural log of secant of x plus the constant of integration. Or we may also say negative natural log of cosine of x, because cosine to the negative one, reciprocal of cosine is secant, cosine of x, just in case both of the forms are equivalent. Okay, now let's look at some summary. We did cover, of course, U substitution. That's always the technique that has to be checked. Maybe it works, then we don't need to apply more complicated one. But if the U substitution is not working, we have more tools, more techniques. Integration by parts, some selected trigonometric integrals we cover, that's the types. Trigonometric substitution, important techniques to simplify, especially the radical expressions. Partial fractions decomposition for the rational functions. And integral table or computer algebra system, we didn't really talk about this, that's why please ignore this. Okay, and then I also create like a more details explanation for each of these techniques. You may pause the video, you may look at this. You can also go separately to these sections because we also have a video for each section. And yeah, that's the way to practice. We remember integration by parts, trigonometric integrals, some important formulas, and then sine of x times cosine of x dx, taken to the power of nm respectively, and some suggestion. But we remember it's just the U substitution, and we don't even have to exactly like memorize the technique. It's just the U substitution. You may choose sine of x or cosine of x, and the same will apply for tangent of x times secant of x dx, taken to the certain powers. And we can give some suggestion when it's even, when it's odd. This substitution works, but please just think, please just apply the common sense and use the U substitution. When you see them one more time, sine of x times cosine of x or tangent of x secant of x, please do not use any like tables and reduction like formulas. No, just basically U substitution, thinking about that derivative and this derivative and the rest of the process. Okay, now trigonometric substitution, that's the three typical expression that we may see, and then we have a relevant substitution, and everything is based on the trigonometric identities, because if we can imagine these identities being the radicand, the expression inside the square root, we may rewrite as a one single expression, and then these restrictions, this domain is letting us to simplify square root of cosine square theta. It will be just cosine because cosine is positive. I mean, we can definitely think about this. I know that you practice a lot. And then we have partial fractions decomposition for the rational functions. We have a couple of cases. Case one, just all of the factors are linear. Case two, they are linear, but they are repeated. And case three may include will include irreducible quadratic factors. And that's the way to spread, to create the partial fractions. And then fraction by fraction, we can integrate, okay? And as I said, we will not have all of the cases because that will take just the selected integrals, like Nice, funny integrals. Okay, let's start. Exercise number 1. Now let's speed up. This is fine. I mean, this is really nice to know, yes, to realize this. I can quickly explain. When we have an integral of a rational function, and when we see a function, and luckily we can see the derivative on the top of this fraction in the numerator, then we may say that this is just natural log of the denominator. And you may realize the u substitution is behind. That means I can see the first one is 1 over x plus 1. Derivative of x plus 1 is 1. Yes, that means I am allowed to say this. Okay, let's look number 2. Integral of 6x and 3x squared minus 1. 3x squared minus 1. Derivative of this is sitting on the top, 6x. I am allowed to say that this is natural log of the denominator. If and only if you see the derivative on the top. And then tangent x plus e to the x, derivative of tangent is secant square of x, e to the x is e to the x. I am allowed to say natural log of the denominator. And that means that's how you can be a little bit faster, a little bit more competitive. But let's maybe prove this. We will definitely let u to be x plus 1. du is 1 dx. We can see 1 dx. This will be replaced as a du. Then our integral, it will be 1 over u du. And this is natural log of u, natural log getting back to original variables, natural log of x plus 1. Done. The same for here. U will be the denominator, 3x squared minus 1. Derivative of u, it will be derivative of 3x squared minus 1, 6x dx. That's what we were actually, this is du. Okay, then the corresponding integral is just 1 over u du. The same thing, natural log of u. We can see we have managed to remove that x expression from the numerator, and then we can substitute back the x variable. Okay, and the same, u is denominator tan x plus e to the x. Okay, and then derivative of u, it will be secant square of x plus e to the x dx. And this is sitting and waiting for us to be replaced with the du. Okay, and then the corresponding integral, you may guess, it's just 1 over u, and this is du. Natural log of u, and we may put back, instead of u, the original expression, tan x plus e to the x. Okay, we can see, but we may skip the green part. We may skip it if you remember that this will work. Okay, exercise number 2. Let's see what we are dealing with. We have some integrals and we have some values in the table. Okay, now we have to compute this. Let's focus on part A. Right? We have an integral, definite integral from 4 to 6 to f prime of x e to the power of 3 f of x dx. So we may notice we have a product. However, when we take the exponent as a u, we have derivative. That means this is good for the u substitution. Let's try. It will be 3 f of x. Then du is 3 f prime of x dx. Okay, we do have f prime of x dx, but we do not have 3. I will divide by 3, and then f prime of x dx will be replaced with 1/3 du. Okay, let's see what we have. Let's put the constant outside, and e to the power of 3 of f of x times f prime of x dx. Let's rewrite first. 2 e3 f of x is u, and f prime dx f prime of x dx is 1/3 du. Because we remember, as soon as we make the commitment to rewrite everything in terms of u and x is not welcome together in the integral, unless it's the two variable functions. So we always avoid putting u and x together. Okay, we have 2/3 integral of e to the u du. 2/3 integral of e to the u du is e to the u. And now we need a limits of integration. Okay? We may, let's cross this one because we will solve it on the next slide. We may use the new limits of integration since we have a definite integral with the u substitution. That means this will be a new, let's say, bounds, new bounds, a little bit informal, new limits of integration. When x was 4, yes, then the new u value will be 3 times f of 4. We will just use the substitution, and instead of x, we will replace x with the x value, original x value. And then u will be 3 f of 6. Okay, that's mean wherever we have u, it will be 3. Oh, we can get the values actually, because we have the values. Okay, I'm actually squeezing. Let's maybe put the, then I don't have to write. F of 4, what is f of 4? F of 4 is 10. 10 times 3, 30. That means this will be 30, 30, 30. The first one, I can still put 4. Okay, now 6. 3 times f of 6. F of 6 is actually 6. 3 times 6 is 18. Okay, 18, 18, 18. But this was x. It's still 6. Okay, that means the final answer is 2/3 e to the power of 18 minus e to the power of 30. And I believe we can leave it like this. We may factor out e to the power of 18, but let's leave it. Yeah? Really nice. Okay, let's keep working. Let's do part B. I think I copied this. That means now we will focus on part B. We have derivative. We know that the integral of the derivative is just the original function, derivative of the function. But we have to just be careful. We have an inner function. So I will recommend to doing this substitution. U is 2x, du is 2 dx. That means 1/2 is just the constant, is dx. Yes, we remember we're not solving for dx if x is just if it's a constant. Okay, that's mean now how the integral looks like. F prime 2x was the u, and dx is 1/2 du. We may put 1/2 outside, f prime of u du. Okay, and 1/2 integral of the derivative of the function is just the function, because that will be the antiderivative. Okay, we need a new limits of integration. Let's find new bounds, new limits of integration. When x was 0, then u will be 2 times 0. Also 0. 0, 0, 0, but it's a new 0. If x was not 6, actually 4, u will be 2 times, 2 times 4, 8. Okay, now let's use the fundamental theorem of calculus, f of 8 minus f of 0. Okay, let's actually use the same line. F of 8 is 2. F of 0 is 15. Okay, the final answer is -13. Okay, -13 over 2. This is the final answer. Okay, -13 over 2. I supposed to shift everything nicely up because I didn't, yeah, I like to, but okay, negative 13 over 2. Okay, and let's do part C. We will skip this. Now we see the second derivative. We see x times the second derivative of the function f at x. That means we don't really see the inner function. That means I think the u substitution will not work, but I think integration by parts will be good. Integration by parts, because we have product, u substitution is not working. That means we're trying, we may be still wrong. That means please remember, we don't know sometimes the techniques right away. Let's try u and dv. This will come from the integrand. We will calculate du derivative and we will recover v, anti-differentiating dv. Okay, and u will be we will take x, and second derivative dx is dv, because we can nicely recover v. It's just anti-derivative. It will be first derivative, because derivative of the first derivative is the second derivative. Derivative of x, 1 dx. And now our magic blue pen, uv v du. So let's maybe write this integral here, then we will not run out. uv minus integral of v du, integration by parts. Let's put in, that we will have x, f prime of x, minus integral of f prime of x, times 1, then dx. Okay, we do have limits of integration. Let's maybe integrate the entire. Okay, integral of the derivative is just the original function, because derivative of this function is in the integrand. Okay, that means we finish our integration. And since that wasn't a u substitution and we didn't change the variables, the limits of integration stays the same, because 2 and 6 are the x value and everything is in terms of x. Okay, let's replace x with the upper bound, 6 times f prime of 6 minus f of 6 minus the same thing for the lower limit, 2 times f prime at 2 minus f of 2. Okay, 6 times f prime at 6 is, f prime at 6 is negative 3. F of 6 is actually 6. We knew this. Minus 2 times f prime at 2 is negative 2. F of 2 is 13. Okay, what we have? We have negative 18, negative 24, and then we have negative 4 and negative 13. It will be negative 17, however, subtracting will be positive. And then what we have, negative 7, if I am right, we may check, because always the last step, the basic arithmetic, it's actually not that basic. I think it's 7. Okay, negative 7 is the final answer. Okay, we did some techniques of integration through like the table values. Okay. Oh, we have another one, but what I can do, I can leave it this one for you. Okay, it's the same concept. I will add my solution. That means you may pause the video, you may work on them, you will check if you good, okay, but I will add the writing, the solution. Please test yourself. I will be so happy and proud of my students if you can get these answers. Okay, A, B, and C. You have, okay, now let's just solve the other. One question with the table values is enough. Okay, exercise number 4, I have this integral, natural log of x squared plus 8 dx. We remember when we have, like when we see the inverse function, or actually this is also natural log, is the inverse of the natural exponential function. But u substitution will not work, because even if we let u to be that inner function, We know the derivative will contain x, and we do not have that x to cancel out or maybe to rewrite. I mean, we may try, but we will probably realize that this is the mistake. And we remember we have to correct our mistakes right away. Then the life is easier. Then we have to find different way. That's we will do multiplication by 1. We remember that method, and we will do integration by parts. I mean, integration by parts. Okay, u dv. And we will compute the derivative. We will compute the antiderivative. Okay, let's see. This has to be natural log of x squared plus 8. Domain is all of the numbers. We are okay. And this will be 1 dx. Derivative of natural log of x squared plus 8 is 1 over x squared plus 8 times derivative of this inner function, 2x dx. Antiderivative for 1 is x. Okay, magic blue formula, uv v du. uv integral of v du. Let's see what we get. I hope we will have easy integral. Okay, then uv is x natural log of x squared plus 8 minus an integral of x times 2x over x squared plus 8. It will be 2x squared over x squared plus 8. Oh, interesting. It's a rational function. Let's see what case. I will copy this. First of all, I will factor out 2. Okay, x squared plus 8. So we can definitely see the denominator x squared plus 8 is quadratic irreducible, no other terms, no other factors. So we may think right away about the arctangent. Arctangent is involved. But we have to be careful. Arctangent we cannot say right away because we still have a function, we still have a variable. For arctangent, we have to have a constant. So we can do 2 things. We can do the normal, traditional way, looking at this as a rational function, improper rational function, because the degree is the same. We may use the long division. We can divide numerator by denominator. We will have a quotient, the whole part, plus the fraction, and then definitely the constant will be on the top. But I can show you a small trick, since this is like, I will add 8 and subtract 8. It's almost like a long division. Let me copy this, minus 2. And now we will have an integral of x squared plus 8 over x squared plus 8 minus 8, because we can see I will keep 1 8 at one fraction and the other 8 at the second fraction. Oh, everything is dx. And as we can see, it's still plus 8 minus 8. I didn't change anything. But how nice I simplify and make myself able to use, okay, this will be x squared plus 8 over x squared plus 8 is 1. Okay, I can still keep it. Now maybe I can split for 2 integrals, because subtraction, integral of subtraction is the subtraction of 2 integrals. So I mean, this will be 1 dx minus integral of 8 over x squared plus 8 dx. And that 8 I can actually put in front of the integral, and then we will use the arctangent formula. Okay, that's now I did eliminate the variable from the top. I'm trying to keep nice order, but I'm running out of space. Okay, integral of 1 is x. 2 times x. I will distribute 2, because we have to remember actually negative 2. Now, negative and negative will give us positive 16, 8 times 2. And now we have integral not exactly, we have an integral not exactly x squared plus 1, because this is arctangent of x. We all know this. but we do have an integral x squared plus a squared. Okay, so I mean, it is also arctangent, but that x is affected by a this way, and the entire function is affected by a this way. Okay, so now we just need the square root of 8. Unfortunately, it is square root of 8. It's irrational number, but we can still, yes, we can still manage. That means this is that 8, that a squared. Then we will have 1 over square root of 8 arctangent x over square root of 8. Okay, plus the constancy. Let's just get the final answer. I mean, we don't have to rationalize. We may. Let's maybe write x squared plus 8 minus 2x, and then plus square root of 8 is actually 2 root 2. Yes, 2 root 2. That means I can 16 divide, it will be 8 over square root of 2, which we can still write a little bit nicer. Arctangent, and then this will be x over 2 root 2 plus the constant of integration. I can rationalize. That means this will be 8 times square root of 2 over 2. This will be 4 square root of 2 arctangent, and this will be square root of 2. We don't have to really do this, over 2 times 2, 4, plus the constant c. Okay, that means this looks like a beautiful final answer. Okay, the last box, which I can use maybe yellow, it's a final answer. Okay, we can see we have a couple of things. We look at the green color, look at the purple color, and the red is the partial fraction. Blue is the formula for partial fraction, not for the partial fractions, for the integration by parts, Okay, really nice, yeah? Nice integral containing a couple of concepts. Okay, let's keep working. Now we do have a trigonometric. Okay, we have trigonometric integral. That's what we can do. We may keep that 6x, but maybe not. Maybe let's use the u substitution. Okay, we will use the u substitution just to make sure that, I wanted to write 1/6, just to make sure that we will have 1/6 du is dx. It's a constant, but let's see. So when we have cosine to the power of 7, cosine to the power of 7, it will be u, and dx is 1/6 du. Okay. Okay, that means now what we can do, we have an odd exponent. That means we will rewrite as a cosine of u to the power of 6 times cosine of u du, and a single one. And now, well, it will be a little bit crazy, but let's do it. We may think that that formula supposed to be rewrite in terms of sine, because derivative of sine is cosine. I mean, I will keep this as I will. Oh, we need another. Actually, let's just change the variable. Let's say t substitution, okay? Because we will have another one, dt. That means this will be cosine of t, cosine of t, cosine of t, dt, and dt, because we will have another dt. Okay. So we will, yes, now we will use the u substitution. That means I really want this to be du, but then I need the entire integrand, except this one, to be rewrite in terms of sine. Let's try. I don't know if we can manage. I know cosine square of t can be rewrite in terms of sine, but then this will be cube. Right? And let's just still copy cosine of t dt. We actually don't need this parenthesis because we know that this belongs to I don't know why I'm writing this. Some of us are writing. Okay. It's me now. Cosine square of t. I know that everybody will tell me that is 1 minus sine square of t. Perfect. I mean, we may let u to be sine of t, and then this is waiting to be cancelled out. And this is waiting to be du. Okay, let's do it. I will maybe use different color. I will let u, another substitution, to be sine of t. Du is cosine of t dt. We did this. That means cosine of, let me write one more time, 1 minus u squared cube. That's a little bit crazy, but we will do it. And then cosine of t dt, we may see is du. We have a nice integral in terms of u. Let's expand this. Let's FOIL 1 minus u squared cube. I hope you remember how to cube. Okay, when we have a minus b, let's say plus cube, then we will just start from the highest power. That means we have always a times b. That means a cube and b to the power of 0. And then a squared, b to the power of 1, a cube, b to the power, oh, wait a minute, I did something. 1, not cube, I am decreasing. Yes, you can see I'm decreasing a cube, a squared, a to the power of 1, and then a to the power of 0. But now let's correct b to the power of 0, which is 1, b to the power of 1, b to the power of 2, b to the power of cube. That's we can see the pattern. The first, a, it's the exponents are decreasing, 3, 2, 1, 0. B are increasing the exponents, b to the power of 0, b to the power of 1, b to the power of 2, b to the power of 3. The only thing that is missing, coefficients. And coefficients we will take from that Pascal triangle, but I can tell you it's 3 and 3. Okay, and if it's addition, all is addition. But when we have subtraction, we follow the same thing. A cube, it will be 3a squared b, 3a b squared, and then we will put it the signs b cube. Okay, what we can do wherever, because we can see negative b, subtracting b, wherever b has a power to odd power, it will be negative 1. This is squared, then will be positive, and this is cube. Okay, that's when we have to use the formula. Let's see. That means our a is 1, our b is u squared. We have to be careful. That means this will be 1 cube minus 3 times a squared times b. A squared is 1, and b it's u squared. Okay, now plus 3. A is 1, b squared. That means I have to square u squared, 4, and minus the last quantity cube. U squared cube will be u to the power of 6. I think it's not bad. You can also FOIL. Yes, you can basically take 1 minus u squared times 1 minus u squared times 1 minus u squared. But I use the polynomial. Okay, and now it's just the integration. Integral of 1 du is u. Integral of 3u squared will be just u cube. And then this integral will be 3u to the power of 5 over 5, u to the power of 7 over 7. And the only thing that we have to do at the end, u was sine of t. So instead of u, we will replace every single u with sine of t, and then t was 6x. Let's do it everything at once. U is sine of t, but t is 6x. U is sine of t, but t was 6x. And then 3 over 5. U is sine of t, but t was 6x to the power of 5. And then one more, sine to the power of 7, 6x over 7, plus the constant of integration. Okay. Also nice integral. Good for the homework assignment. Yeah, it's a little bit maybe longer for the exam type, but make sure that you can deal with each component. Okay, what else I have? Oh, I have something like this. Let's see what we can do. Yeah, we can see they are a little bit, because these integrals are showing that we don't have to really have some formulas. We can use all of the techniques that we know and try to solve it. We may do similar. That's mean what? It's not a typical that we cover sine secant times tangent. I can maybe split this like this, secant square, secant square. Okay, now we know that the derivative of tangent of x is secant square. I mean, I can say this, secant square of x over tangent of x, and I can hold that one of the secant square to be du, if we let u to be tangent. But since we will let u to be tangent, would be nice to rewrite secant square in terms of tangent. I mean, this will be u, this will be du, because we know I can even write du is secant square of x dx. Perfect, that's the du. But we still have to make sure secant square, we know that is equal 1 plus tangent square. Oh, I don't have to use the blue color. Okay, now we're ready. 1 plus tangent is u. That means we will have u squared. Square root of tangent, square root of u. And this is basically du. And now it's relatively nice integral. We may avoid the quotient. Okay, and this will be u to the negative half. And this will be u to the power of 2 over u to the power of 1/2. 2 minus 1/2 is 3/2. Okay, and we may integrate u to the power of negative half. Integral is u to the power of half over 1/2, 2 square root of u, and this one will be u to the power of 5/2. Maybe I can keep it u to the power of 5/2 over 5/2, multiplying by the reciprocal. Okay, but let's do, since I did the root notation, let's also do the root notation. And u is tangent of x plus 2/5. U to the power of 5/2 is square root of u. U is tangent to the power of 5. Beautiful final answer. Yeah? Also, not typical, but testing if we can use that u substitution. U is tangent or u is secant. Okay. Okay, another one. If this session seems to be too long, you may stop at any point and come back later. Right? Or you may pause, you may try to solve it. Just use this video. Please use this video as a practice problems, and yeah, try to solve them. They are really nice, yeah, brain exercise. Okay, multiple choice looks like I took from our exams. Integral of 1 over 1 plus x squared to the power of 3/2. I mean, power of 3/2, it's indicating that we may apply, we see the root, we may apply the trigonometric substitution. 1 plus x squared, we know that x will be tangent. Yes, tangent theta. Dx is secant square theta d theta. Let's rewrite everything in terms of theta. It's the reverse substitution. Okay, 1 plus tangent square, everything to the power of 3/2, and dx is secant square theta d theta. Okay, let's simplify. I can put actually secant square theta on the top. 1 plus tangent square is, of course, secant square, but we do have square root and still extra power. What we have? secant square theta. Secant square theta under the square root, it will become secant, and we still have that cube, but we know the domain will let us, and because secant is a positive, we will just, since we're using some inverse theta, it's only from -pi/2 to +pi/2 on that interval. Secant, or you may maybe think about cosine as positive, we allowed to say, like, simplify square root and the squared. We can remove the absolute value. Okay, when we simplify, secant square over secant cube is just 1/secant. And 1/secant is just cosine. So nice. Integral of cosine is actually negative. Am I right? No, I'm not. It's just sine of x. Yeah, we have to be triple careful. I mean sine of theta, because derivative of sine is cosine. But we know that we required to rewrite the final answer in terms of the original variable. Okay, what is sine theta? Let's use our triangle method. Tangent theta was x. We may look at this as a tangent theta as a ratio x/1. Let's use the tool triangle. If this is theta, tangent is opposite over adjacent. If this is x, this is 1. From the Pythagorean theorem, this will be x squared plus 1, but I would like to write 1 plus x squared. We know why. Under the square root is the same what we see in the original. And then having all of the sides, we may read sine. Sine will be opposite over hypotenuse. Opposite over hypotenuse. This is the final answer. And I hope one of the options match is this one. But that's not the important part. Important if it's here. Okay. Okay, let's see what I have, yeah, because we are really nice, also really nice integral. Oh, I have table, but we can do this one. Let's do this one. And okay, let's finish what I was planning. As I said, you may leave it and come back later, yeah, but it's good practice. Another table, but a little bit different. What we see? We see 1 plus quantity squared, probably arctangent, but let's take this quantity. Let's take this quantity. Oh, how can I do this? And let's let u to be this quantity. Du is derivative f prime of x dx. And we can see f prime of x dx is waiting to be rewrite as a du. Let's do it. I mean, this will be 1 plus u squared du. So nice. Integral of this is arctangent of u. Right? We need a new limits of integration. New limits of integration. I will write new bounds. New bounds. If x was 2, we can see, then u is f of 2. Yeah? And f of, because we're using the f of 2 is 0. Okay, that means from 0, 0. Now, when x was 5, then the new bound u will be f of 5, because that's my substitution. F of 5 is 1. Oh, we like that limits for arctangent. Okay, arctangent of 1 minus arctangent of 0. Tangent for what angle is 1? 45. Tangent for what angle is 0? 0. Final answer is pi/4. Excellent. Okay, let's keep working. Oh, we know this. We don't even have to do it, because we actually had this. I supposed to maybe put this in before the natural log. Yes, what we had. Arctangent of x. That's it. And this one, it is arctangent of x, but x is affected by this 3 1/3. Okay, maybe I can put the argument like this. Okay, done. That's what we have to know. Okay, and then I have, too many. Okay, we can solve it this one together and you will solve it alone. And that's everything. Okay. what we see rational functions, 7.5, I think, yeah, partial fraction decomposition. But when we start looking at the denominators, they are not like, we cannot factor out. They are irreducible. That's the irreducible quadratic expressions. That means let's see if it's irreducible. We remember arctangent will be involved. That means let's complete the square. We have, because I need the quantity squared plus the constant. X squared plus 6x, and we know that we will be missing 6, if we remember the algorithm. 6, the coefficient of x, 6 divided by 2 is 3, 3 squared is 9. That's how we always can get the third quantity. And then if I added 9 only and I added 10, it will be 1. Okay, let's rewrite this. X plus 3 squared plus 1 dx. And if we will let u to be x plus 3, I can even do it. U plus 1, derivative of u, like du, will be dx. And we don't have to, we can say right away, because always when I will get du is dx, it's sometimes a little bit alarming because it might indicate that we're not changing anything, but actually we are changing, okay? And that's what we have. Arc tangent of u, but we will say arc tangent of x plus 3. And because it's really nice integral. That means I know we may have this integral, make sure that we know completing the square method. Okay, this one is similar, quadratic irreducible. However, we do not have constant on the top. We just have something. I mean, the expression that depends on the variable. It's like the function. And it's proper rational function. But do you remember the formula that we start our session? What I see rational functions, polynomial on the top, polynomial on the bottom. And what is the derivative of the denominator? 2x plus 6. That means I can say right away, this is the answer. That's it. Because if I will let u to be this, du is sitting and waiting on the top. And as we can see, this will be du, which actually I can write it down 1 over u du. Natural log of u, and u is that whole expression from the denominator. Okay? So please, yeah, I think I have the set this one. Yeah, you may try to work it out. Okay. Yes, thank you very much. And that was really nice review of kind of like all of the integrals, because we touch almost all of the techniques. Enjoy the integration. Thank you.